Welcome to Lecture 3 in Valence Bond Theory. I am your friend Dr. Atul Nagpure, Assistant Professor. So in this lecture, we will discuss various features of complexes having coordination number 3. And in this complex, we always expect that the hybridization should be Sp2 with a trigonal planar geometry. Let's start our discussion. So when we have Sp2 hybridization, one s atomic orbital of the metal, which is empty, react with the px and py pure atomic orbital of the metal. Remember that s, p and this p, all three are empty pure atomic orbital of that metal. Now these three will undergo the process of hybridization in order to give a 3 Sp2 hybrid orbital. You can see here, first Sp2 hybrid orbital, second one and the third one. You might have realized one important point here, that all Sp2 hybrid orbital has the nearly same symmetry and equivalent energy. On the other hand, if I take s atomic orbital, the s atomic orbital has the relatively less energy in comparison to a px and py atomic orbital. Moreover, the s atomic orbital has a spherical in shape, whereas the px and py has a dumbbell shape. If you compare the shape of this 3 atomic orbital and this hybrid orbital, you conclude that the shape has changed drastically, and this is nothing but the process of hybridization. So from the pure atomic orbital, we are getting 3 Sp2 hybrid orbital which has a nearly same symmetry and equivalent energy. Now what they will do, they will try to arrange in the space in order to get a trigonal planar kind of geometry. So if you look at this, the first, second, 3 lobes, now they are arranged in the space just to get a trigonal planar geometry. So let us imagine this is our complex which has trigonal planar, right, geometry, and distance between these two, first and second, will be 120. From here to here we have 120, and from here to here we have 120 angle. So that means when we have Sp2 hybridization, we always expect the angle will be always 120. Now let's take some example of this. Here I have given some example. Here first Mercury complex, and Mercury complex in this coordination number equal to 3, and here Mercury is in a +2 state, alright, and this is nothing but a 5D10 system. Similarly here, this is again a coordination number 3 complexes which has a platinum in 0 oxidation state, since these trivinyl phosphines are the neutral ligand, and this is again a 5D10 system. Moving towards next. In this complex, the copper is carrying a copper +1 charge. This is copper +1 charge, and this is now again a 3D10 system. In this we have Cl and Tu. Tu is actually thiourea. Thiourea. This is a ligand. So this 2 thiourea and 1 Cl. So all these complexes are the example of the trigonal planar geometry. Now let's discuss how the bonding occurs in these kinds of complexes. So for that I am taking one example, and we will discuss how bonding occurs and what are the arrangements in the interaction between metal and the ligand. So let's take one example here, like Mercury complex. here we have a mercury complex and I3 minus 1 charge. As I told already, this is a mercury plus 2 and hence this is now a 5-detailed system. Okay, now since we have 5-detailed system here, so what are the orbital left? So we have now 6s which is empty and 6p is also empty. Now I can draw that we have 5d10. So 1, 2, 3, 4. So this is 2, this is 4, this is 6, this is 8 and this is 10. This is my 5d10. And we have one 6s which is empty and we have a 3p. Sorry, we have a 6p again empty. So the point is that now you take one 6s atomic orbital and these two. We have, let's take this is a px and this is py and this is a pz, and now they will undergo process of hybridization and they will give Sp2 hybrid orbital. And once they give Sp2 hybrid orbital, what happens? The ligand molecule will try to form the bonding. Now we have I minus ligand here. I'm writing here we have I minus ligand, and this I minus ligand will give a 2 electron to the empty hybrid orbital, and that's how the bonding will take place. This arrow shows electron density is transferred from the ligand to the hybrid orbital. Now they will arrange in this way. We have mercury, so this will arrange in this fashion. So we have iodine here, iodine and I, and if I take a whole complex, the whole complex now will have a -1 charge. Okay, now angle between these two, we expect will be always 120 degree. But now question is here that do we have always 120 angle? And answer is no. Please remember that there are few complexes in which it has been observed that angle is not 120. So let's take this. If you compare this complex now, this complex we expect this is a perfectly trigonal planar complex and angle is 120 in all the direction. But imagine that in these trigonal planar complexes, this is non-bulky ligand, this one, and these two are the bulky ligand. And when they are bulky ligand, what they will do, this ligand and this ligand will they try to oppose each other, and that's how they will create a steric crowding. So when we have steric crowding, they will try to go away from each other, and hence now you can see my hand, they will try to go from each other, and that's how the bond angle start deviate. So what we expect? We expect if we have metal, and this is what we always expect, that this is ligand, and this is ligand, angle is 120, but the ligand, if is bulky in nature, what they will do, they will try to form these kinds of complexes, and this is nothing but a kind of T-shaped complex. And here the angle between these two, if I take the angle between these two, this angle will be always more than 120. Okay, so remember the point. Since we have bulky ligand, the angle can be 120. Now I am giving next example, in that the angle is a different angle. So let's take, this is my trigonal planar complex, and we expect that angle should be 120 here. But now what happened if I'm having a bulky ligand? It has been observed that sometime we have seen a T-shaped kind of complex, and Y-shaped kinds of complexes also has been observed. Y-shape means if I take the metal and the ligand here, they will try to form a Y types of complex. And because this, if I'm having again bulkier ligand, so if I take bulkier ligand, this will go for the T shape of the complex. If I take this kinds of ligand, again if I increase the size, this ligand will create a steric crowding here, and this two, so this and this two will try to come close together, and that's how they will form a Y kind of complex. And if I find the angle between these two, this will be less than 120. So please keep in the mind, there are a few complexes are there which can deviate from the 120 angle. Now let's discuss now interesting part. We always expect that when we have coordination number 3, that geometry will be always Sp2, right? This is what we know, we have read from the Google or from the notes or many reference books. Now in this lecture, I will try to explain what are the different possibilities are there. There is one research article in the Royal Society of Chemistry which is published nearly 3 to 4 year back, and they discuss the possibility of Sp2 hybridization. So listen very carefully, I am discussing Sp2 hybridization. Sp2 hybridization in coordination number 3. This is what I am discussing, and this is a very important concept. So when I am having Sp2 hybridization, in that research work, they have prepared various transition metal monolayer with hexagonal lattice structure, and they found that when we have d orbital, let's say we have d orbital and s orbital and the p orbital, when this d orbital has equivalent energy to s orbital and the p orbital, this d orbital can take part in the bonding, and that's how we have Sp2 hybridization. Now if I discuss in terms of crystal field theory topics we will discuss later, but remember that there is a crystal field splitting diagram for the d orbital when we have trigonal planar kinds of geometry. So according to crystal field theory, it says that when we have coordination number 3 and trigonal planar geometry, the dxy and dx square minus y square, these two d orbital can take part in the bonding when we have coordination number 3, and remaining will be the s orbital. So whatever I am discussing here, this Sp2 means out of that, one will be s atomic orbital of the metal, second will be dxy atomic orbital of the metal, and third will be dx square minus y square of the metal. The questions here, we have 5 different d orbital: dxy, dyz, dxz, dz square and dx square minus y square. Why is only dxy and dx square minus y square taking part in this bonding? That can be answered very well by crystal field theory. That part we will discuss later. Now in that research work, they have taken metal, I am writing here metal, they have discussed various aspects, and metal was a chromium metal and a tungsten metal and molybdenum metal. So these was the metal. So they has prepared the kind of layer structure, and they has confirmed that when we have coordination number 3 in kind of layer structure, we have possibility of Sp2 hybridization. So for this I will going to give a link so that you can refer from the description box. Similarly, this is actually for the coordination number 3. So when remember that when we have coordination number 2, in coordination number 2, what we expect when we have coordination number 2, we expect that it is always should be Sp hybridization. Am I right? This is what we expect. But the various research study and investigation has proven that there is a possibility that SD kind of hybridization is also possible. So this is you can make a note of that. We can have SD kind of hybridization, and when we have SD kind of hybridization by crystal field theory, the d orbital involved will be here dz square. Okay, so for coordination number 2, dxy and dx square minus y square. And for coordination number 2, when we have SD kind of hybridization, the dz square orbitals are involved in the bonding. For this explanation, I will give a link. You can read that. It is a very interesting part. Now let's move towards next topic. In the last video, I have told it is difficult to find out the coordination number only from the molecular formula. Just giving one complex here. Suppose we have a potassium copper cyanide complex, right? And here you will say that, sir, this is a coordination number 2 complex, but this is actually a wrong. The coordination number 3 is the right answer. Reason is that this is a single chain polymeric form, and we have here cyanide and CN kinds of structure, and this is a polymeric form. So one ligand, second ligand, and third ligand, and that's how the coordination number 3. The point is that you cannot judge simply by molecular formula what is the coordination number. Similarly, I am giving some complexes. Cesium CuCl by 3. In cesium CuCl by 3, you may say that, sir, this is coordination number 3. But again, because we have 3 Cl ligand, again this is wrong, because the real coordination number is a 4 coordination number, because it is an infinite single chain, and structure we have this type Cl we have, and we have a Cu. Here we have a CuCl by 2, and again Cl, and this is a kind of single chain structure, and we have one Cl, one second, and this 2, so we have 4 Cl, and this is nothing but a kind of coordination number 4 complex. Let's move towards further. Let's take next example. Next example, I am taking potassium CuCl by 3. Now from the stoichiometry point of view, you will say this is a coordination number 3. Again, this is wrong. The coordination number is actually 6 for this complex. And why it's 6? This is actually a double chain compound, and this is this kind of a distorted octahedral kind of complex. This is distorted octahedral kinds of complex. Now moving further, let's take example again. Ammonium cadmium chloride complex. Ammonium cadmium chloride complex. From the stoichiometry, you will say this is coordination number 3. Again, this is wrong. Here it earlier was 6, and again here we have a coordination number 6 is the right answer. And this is undistorted. This is actually undistorted. Distortion is very less here, and undistorted octahedral complex. The point I am trying to tell, you must have a knowledge of the structure information when we are discussing the chemistry of the coordination compound. Now further, I am discussing the complexes of HMDS ligand. In the previous video, we have discussed this complex HMDS, and you know HMDS means we have hexamethyl sila chain. And structure, you know that we have seen in the last video, we have silicon and we have silicon, and we have here methyl, and here again methyl. This is HMDS complex, and N carry negative charge. Remember that low coordination number like coordination number 2 and 3, they are stable when we have bulky ligand, and HMDS is a kind of bulky ligand which stable the complexes in a low coordination number. So when we have these kinds of ligand, generally what has been observed that a scandium plus 3 ion, titanium plus 3 ion, vanadium plus 3 ion, chromium plus 3 ion, a manganese plus 3 ion, and again iron plus 3 ion, and a cobalt plus 3 ion, they are form such kinds of complexes, and the formula will be HMDS by 3. Okay, so metal can be of any type, and here we having metal plus 3 charge, and coordinate sphere have minus charge because each ligand has a -1 charge. Complex is neutral. Not only that, many lanthanides. Remember that a metal M plus 3 can be also a lanthanides elements even, and lanthanides are various types of lanthanides can form the complexes. We have lanthanum, cerium, lithium, then we have neodymium, then we have samarium, then europium and gadolinium, then dysprosium, holmium and lutetium. These kinds of metal ion in plus 3 oxidation state can also form the complexes with HMDS ligand. Moreover, some of the actinides also form the complexes, and there are only few. We have uranium, neptunium, and etc. So only few are there which can form the complexes with the HMDS ligand. So finally, we have discussed various aspects of the coordination number 3 complex, geometry, structure, and various features. I hope that you like the video. Thanks for watching. Signing off, Dr. Atul Nagpure.